Now let's study section 3.9, base load, intermediate, and peaking power plants. Figure 3.26 shows an example of weekly load fluctuations for a hot summer day in California. We can categorize the power plant as a base load power plants, intermediate power plants, and the peaking power plants. From this figure, we can see that the demand of electricity vary considerably from the day to night. It also exhibits the weekly patterns with a diminished demand on the weekend, as well as seasonally with some utilities seeing their annual highest load on a hot summer day. It suggests that during the peak demand, most of power plants will be operating. Well, in the valleys, which means the load is low, there are many likely to be shut off. Now, for utility planners, the important question is what combination of power plants will most economically meet the hourly by hour power demand of their customers. So some power plants, such as coal-fired plants, as well as hydroelectric power plants, are expensive to build, but relatively cheap to operate. So these power plants are usually run as a baseload plants. Other power plants, such as simple cycle gas turbines, are relatively inexpensive to build, but expensive to operate. So they are most properly used as a peaking power plants. Other power plants, such as a combined cycle power plant, have characteristics that somewhere in the between. Though these power plants are used as intermediate load plants. The intermediate load power plants are often run for the most of the daytime, then cycled as necessary to follow the evening load. Section 3.9.1, Screening Curves. A simple model of the economics of a given power plant takes all of the costs and put them into two categories, fixed cost and variable cost. So we usually use a screening curve to study the cost of the power plant. The fixed cost must be spent even if the power plant is never turned on. So the fixed costs include capital costs, taxes, insurance, and the fixed operation and maintenance costs. Variable costs are associated with actually running the power plants. They are mostly fuel plus operations and maintenance costs. How to develop the screening curves? The first step to develop a screening curve is to show the annual revenue required to pay fixed and variable cost as a function of hour per year that the plant is operated to find the optimal mix of the power plants. The capital cost of a power plant can be annualized by multiplying it by a quantity called the fixed charge rate. The fixed charge rate accounts for interest on the loans, acceptable returns for investors, fixed operation, and O&M charges, taxes. The fixed charge rate depends mainly or primarily on the cost of capital, so it varies as interest rates change. The fixed charge rate is usually between 11% to 18% per year. So equation 3.18 shows the annual fixed cost computation equation on per kilowatt of rated power base. So the fixed cost is equal to the capital cost multiply the fixed charge rate. This has been converted into the per kilowatt basis. To analyze the variable cost depends on the unit cost of fuel, the operation and the maintenance cost for actual operation of the plant, and the number of hours per year the plant is operated. So the equation 3.19 shows the variable cost is equal to the fuel cost per BTU multiply the heat rate. So convert the fuel cost in terms of per kilowatt hour plus the operation and maintenance cost per kilowatt hour, and then the sum of this multiply the number of hours per year that the plant is operated. In this 3.19 equation, we assume that the power plant runs at full rated power, but no power at other times. Adjusting for less than full power is an unnecessary modification that will be introduced later. Also, 3.19 assumes that the fuel cost is fixed, but actually the fuel cost should be adjusted to account for fuel escalation and inflation. To study our current to investigate the cost purpose, those modifications are not very important, so we'll assume to use the fixed fuel cost. Now let's use say example 3.3. Find the annual revenue required for a pulverized coal steam plant using parameters given in the table 3.3. Assume there is a fixed charge rate of 16 cents per year, or 16% per year, and assume that the power plant operates at the equivalent rate of full power for 8,000 hours per year. Now, the question is, what should be the price of electricity from this power plant? So if from this table, we can see that the pulverized coal steam power plant, the capital cost is 1,400. The heat rate for this pulverized coal steam power plant is 9,700. The fuel cost is $1.5 per million BTU, and the variable operation and maintenance cost is 0.43 cents. It's 43 cents per kilowatt hour. But this table also shows the fuel and the capital cost, heat rate, fuel cost, and the variable operation and maintenance cost for other type of power plants. We can see that the hydroelectric power plant has the highest capital cost, because to build hydroelectric power plant required to spend significant amount of money for building the dams. So the capital cost for the hydroelectric power plant is the highest. And then we can also see the fuel cost for combined cycle combustion turbine and the gas turbines are very high. It's a $4.5 range. It's about 3 times of the coal type of the steam power plant, because this is because this power plant uses natural gas. And compared with coal power plants, the combined cycle combustion turbine power plant has a relatively low capital cost. Since this example asks us to calculate for polarized coal steam power plant, so we'll focus on this power plant as example to calculate the price of the electricity. Now, we can see the capital cost of the polarized coal steam power plant is $1,400 per kilowatt. So the annual fixed rate required could be, the fixed cost is 1,400 per kilowatt, multiply the fixed charge rate is 0.16 per year, which is equal to $222 per kilowatt per year. So convert is down to the yearly basis, so that we can combine this value with the operation cost, since operating cost is also based on the yearly basis. Now, let's look at how to calculate the operation cost. The variable cost for the fuel and the operation and maintenance cost when this power plant is operates 8,000 hours at full power. So the variable cost is equal to the fuel cost is $1.50 divided by 1 million BTU, multiply the heat rate 9,700 BTU. So we can obtain the fuel cost per kilowatt hour plus the variable cost per kilowatt hour, and then multiply the total operating hour 8,000. We can obtain the variable cost is equal to $150.80 per kilowatt per year. Now we have calculate the fixed cost is $222 per kilowatt hour per year. The variable cost is $150.80 per kilowatt per year. So for a power plant, if they generate for 1 kilowatt hour, the capacity is 1 kilowatt, therefore they operate 8,000 hours. We can obtain is 8,000 kilowatt hours, and the price will be the capacity 1 kilowatt multiply the fixed cost plus the variable cost, and then divided by the energy, the total amount of energy generated. So we can obtain the price for this pulverized coal steam power plant is 4.69 cents per kilowatt hour. What does this mean? This means that this pulverized coal steam power plant will require minimum 4.69 cents per kilowatt hour in order to meet their revenue requirement. So these power plants will cost or the electricity price generated by this power plant should be 4.69 cents per kilowatt hour. In the above example, it assumed that in a year with 8,760 hours, the power plant would operate at full power for 8,000 hours, and there's no power for 760 hours. So probably 760 hours are the maintenance hours. So the same 8,000 kilowatt hour per year could be the result of operating full 8,760 hours, but it's not always output at the full rated capacity. So which means at each hour, the power or the power generated by this power plant could be less than it is on capacity. So, together, the total amount of energy generated by this power plant is 8,000 kilowatt hour. Now, we're going to introduce a new technical concept called the capacity factor. If we know the annual output and we know the rated power, the rated power multiply 8,760, then we can obtain the total amount of energy generated by this power plant if this power plant run always at the rated power for the full year. However, it's not always this power plant run at the full rated power. Therefore, the capacity factor is equal to the average power per kilowatt hour multiplied 8,760 divided by the rated power multiplied 8,760. So it's equal to the average power divided by the rated power. So the capacity factor is the ratio of average power to rated power. It's also the ratio of the annual generation amount energy divided by the total amount of energy when the generator operates at the rated power for the full year. Figure 3.7 shows a total revenue required by the coal power plant as a function of its capacity factors. As we can see, x-axis shows the number of hours in a year. The y-axis shows the revenue, and the top line shows the capacity factor. So which means when a power plant runs at equivalent 8,000 hours per year at full rated capacity, that is equal to the capacity factor is 0.913. This when the power plant, even the power plant output at zero, because to build a power plant we have the fixed cost, so we can obtain the starting point of this privileged steam power plant is $222 dollars per kilowatt hour per year. Now the slope shows the variable cost, which is 0.0189 per kilowatt hour, which is 1.89 cents per kilowatt hour. So as the operating hours increase, the cost or the revenue required by this steam power plant also increase. And since this power plant, the number of hours is 8,000, so this point is the total amount of revenue required for this power plant. And then from this point to the main point, the slope of this line is the average cost. So the slope line combines both fixed cost and variable cost, shows the average cost of this coal steam power plant is 4.69 cents per kilowatt hour. The screen curve generated by the characteristics of different power plants based on the same coordinates axis and provide the basis for the optimal combination of different types of power generation models. If we put combined cycle power plant and combustion turbine power plant also into this screen curve figure, we can see that, as we know, that the capital cost of coal steam is very high, and then the variable cost is cheap, it's low, due to the cheap coal. The combined cycle and the combustion turbine have a relatively low capital cost. However, their operation cost is high, or the variable cost is high, due to the use of expensive gas. Now, when we plug into this figure, we can see there are a number of cross-sections. This cross-section shows when the power plant operates less than 1,675 hours. We know the combustion turbine power plant has the lowest value. So the combustion turbine are least expensive. So if it is operating less than 1,675 hours, then we prefer to use combustion turbine. But if this power plant runs over 6,565 hours, and this is the coal steam power plant became the cheapest. And during the between 1,675 hours to 6,565 hours, the combined cycle power plant is the cheapest. Section 3.9.2, load duration curves. Here is another new concept, load duration curves. We know that for each hour, the power generated by the power plant can vary. The load of each hour can vary, and it's not always the same. For a whole year, the load has also 8,760 hours. If we rearrange this load curve from the highest load down to the lowest load, now this line is called the load duration curve. A load duration curve is simply the hour-by-hour load curve rearranged from chronological order into an order based on the magnitude. And the area under the curve is the total energy kilowatt hour generated. This is a smooth version of load duration curve. We will see that the load is always between the 2000 to 6000. Since the minimum amount of load is 2000, the highest load is 6000. And if this is a line, if this is a 5000 load, we can see the number of hours is 1000. What does this mean? This means that the load is greater than 5000, has about 1000 hours. Now for this line, when the load is 3000 and then the number of hours is 7000, which means the 7000 hours the load operates more than 3000 megawatt. The load in between 3000 and 5000, the amount of hours is 6000 hours. When we bring the strain curve and the load duration curve together, we can come up the estimate of the optimal mix of power plants. As we can see from here, since if the power plants operate less than 1675 hours, the combustion turbine is the cheapest. So if we find the load curve at 1675 hours, then we can see the number of the the load that's to be served is should be between above 4700 megawatt to 6000 megawatt, right? So this means that we need 1000, the difference between these two is 1300 megawatt. So we need 1300 megawatt combustion turbine power plant. So these are the area, since the combustion turbine runs under the 1675 hours is the cheapest. So this area should be supplied by the combustion turbine. And how much capacity that needed? Capacity of the combustion turbine is the difference between the load demand. So the combustion turbine capacity is required is 1300 megawatt. Similarly, for between the 1675 and the 6565 hours, if this is a 6565 hours, we can see between these two, the demand, the load demand is from 3500 megawatt to 4700 megawatt, and the capacity that is required for the combined cycle power plant is 1200 megawatt. Now for less than, well, for hours above 675, so those are the area the coal has the cheapest, provided the cheapest solution. So which means there's a 3500 megawatt load that need to be served by the coal power plant. So the capacity of the coal steam power plant should be built as a 3,500 megawatt. So this come up the combination of each type of the power plant and how much capacity that should be built in order to serve the annual load. Now, since the year has a 8,760 hours. Now, the total amount of energy below the curve the total amount of energy should be generated by the power plant. So based on this amount of energy to be generated, and this is the full area, the rated power energy, the ratio between the annual power generation with the annual rated power generation is the capacity factor. And we can use this equation to calculate the corresponding capacity factor for each type of power plant. So the rectangular horizon slides correspond to the energy that will be generated by each power plant type if operated continuously and also at full capacity. The shaded portion of the slides is the energy actually generated. So the ratio between the shaded area with the total rectangular area is the capacity factor for each type of power plant. The baseload power plant delivers energy at 4.69 cents per kilowatt hour. And then the intermittent power plant, that is the combined cycle power plant, the combustion turbine power plant, the combined cycle power plant delivered at 6.23 cents per kilowatt hour. And the combustion turbine peakers is required for 12.87 cents per kilowatt hour. This is the value with consideration of the capacity factor, which is has considered the number of the hours operated during the year. So the reason why the peaking shaving price is so high is because it has the low efficiency, which means the low operating hours and the high cost for the natural gas. Based on the resource selection curve, the generation planning can roughly show how much generation capacity needed to be built in order to meet the load demand. Unless the load duration curve has account for a cushion of actual capacity, we call it a reserve margin, because not always the power plant can be operated at the full capacity or at the full hour of the year due to maintenance or outages. So the generation mix estimate have to be augmented, which means it had to be increased to allow for some other conflicting factors. And that the above process is used for the system planning, for the generation planning. To operate at a given time for each power plant, to select the determination of the amount of power generated at each hour, that is called dispatching. So the process of selecting which operator to operate which plant to operate at any given time called dispatching. The dispatching is a system operation function. Since costs already incurred to build the power plants must be paid no matter what, so it makes sense to dispatch power plants based on their operating cost, so in the order of their operating cost, from the lowest to the highest. Now we complete section 3.9.